Thank you very much, Dr. Raja, for this introduction, and thank you that you made this time to come here. Yes, the projector comes up. So, but I also would like to welcome you then directly with questions. So, in case it comes up during the or after the presentation, it's directly very welcome. So, the topic we are talking about here is space-based monitoring, so remote sensing of water quality and bathymetry. And I would like to give you also both the actual status and also the vision that is just short in time before us, because there are some essential improvements in the upcoming time. You will maybe later understand then with respect to which activities. So EOMAP is a private company, spin-off of the German Aerospace Center in 2006, and we are doing monitoring services, especially for aquatic systems, so water quality monitoring, turbidity, water depth, seafloor mapping, for the various applications. So for the oil and gas industry, we are working for dredging companies, for offshore construction, for the topics of impact, baseline monitoring, waterways, pipeline routing, and biodiversity baselines again. So there are various applications, governmental and industry behind that. In this talk, I would like to introduce you with a general idea of the target of remote sensing here, and then with two chapters, mainly water quality monitoring and bathymetry. And in the introduction, well, you know about the general topics. We have a lot of applications to solve that are of economical and social impact, so climate change, floods, waterway construction, dams, and so on. We have a significant impact on people and industry, and we need further tools to improve the monitoring and the baseline monitoring for these things to detect changes over time and space. And the role of satellite services here are, of course, supporting understanding of these environmental processes, but especially to get this really as a reliable tool to delivering objective measures. That was, I think, not so in the past, because remote sensing is easy understandable directly if you look to images, but it is more than just images. There is some specific values behind, and that's what I'm trying to give a look into, what's possible now and also what will be possible. To go this route, there are specific requirements on Earth's observation systems. So they must be area-wide and intercontinental, well, images do, but objective measures do not automatically. So they must cover directly various spatial and temporal scales, and these measures must be harmonized, so objective again. So that means we need somehow standardized products and measures, quantitative measures that are independent on the single satellite sensors. We have lots of them, but to explore them, it must be already independent. So there are some requirements we will come through this presentation. So I would start the first topic. This is water quality monitoring. Give you first an impression of what is the actual status on based on different projects we are doing. So you are, I guess, already in mind that there are different space sensors in place already. We have since decades based on sensors there, working on various scales. So starting 30 years ago, it was more or less low resolution, 1 kilometer, 500 meter. We have a long continuity of MODIS data with 1 kilometer and 500 meter products over here. We have further upcoming sensors for this, which are essentially used for ocean monitoring. We have medium resolution sensors, even more and more. These are partly state-governed, owned, so like EOS, Thailand satellite. We have many more. Vietnamese satellite will start. The Chinese have different satellites in Chile. So there are lots of them. We have further Landsat known by everybody in these scales, and we have upcoming sensors, much more of this type, like Sentinel-2 of the European Commission of ESA, are also very capable, which altogether, so each of them usually gives you provides you with an image all 2 weeks. Now integrating them, you can imagine that it is several times per week if you can integrate these different sensors. So with a low resolution, you know, you have daily, sometimes several times daily coverage. Combining this with medium resolution and high resolution with the commercial satellites, of course, here comes then really the applications rivers, smaller rivers, inland waters, and so on. So a few examples. Dredging monitoring is easy understandable. To dredge the extent of the plume of a dredging ship, but not only this, to quantify this already. So we did this, for example, for several years long for Woodside Energy in Australia for the dredge plume of the Pluto project. There, the savings for Woodside Energy for this was about $1 million Australian. This was mainly based on MODIS and partly then supported with high resolution imagery. So you see here part of the time series. Not here. On the left hand side you see part of the time series with the MODIS resolution. If you go then to the middle, this is rapid eye at one of those dates at 11 o'clock approximate. Then 3 hours later MODIS, you will see the difference in spatial resolution. You may realize already the spatial shift due to the currents, and of course you should realize these colors are not only colors, these reflect physical values of turbidity and related suspended matter, so you can quantitatively compare what is going on here in space and time. Another example, so if you go to inland waters, also for those who are not so well accessible, this measurements are maybe all not so well monitored, but have an impact, social impact on the countries around. So like here with Lake Titicaca in South America. So it is capable to monitor chlorophyll and suspended matter with harmonized measures. So that was the project where the World Bank was interested in, and it could be then successfully delivered. Further examples, we are leading European project funded by the European Commission to establish such inland water services on various temporal scales for Europe. This is not only to establish the service, it also is of course to get harmonized, inspire-conform product lines. So that means that the authorities can directly implement these kind of products in a standard way. They have to, they retrieve now harmonized metadata descriptions. That means can put it into the different systems, can compare each other, and can integrate these products with in situ components and modeling aspects. And the target of this project, which will end in 1 year, is to establish a downstream project, that means commercial project lines. That's what we indeed are doing already now. And it is quite clear that this project already achieved the target by to set up the service line, as you will realize later. But now in the upcoming weeks we are in talks then with the European Commission, with the European Environmental Agency, about how to establish a pan-European service line then here. And we are in contact here with many authorities, as I will show you later, on contractual basis, and also implementing them here in this kind of project. So it is not only about this product, also that users and agencies can work with this product. It requires standardized descriptions, so metadata, OGC conform, and so that you can easily understand. It requires sometimes further software tools that they can handle this kind of data, because delivering to a client hundreds of satellite products is usually an overkill. Even for us, it is starting to get difficult to handle so many data. So it needs some products or software products, for example, in ArcGIS time series analysis, or in QGIS. So that means free software where you also can look to the spatial and temporal view. I will show later. Furthermore, it is especially required to deliver also quality information for each value measured, quality as a standard. And to deliver also the data in various formats, because different users have various demands. So for one of them, they can handle indeed with the professional tools, ArcGIS, such as data. For many of them also it's very helpful to, for example, work with this in Google, with GameZ files, because it's easy handleable. Printouts is still very frequent just as an example, if you go integrate this into Google very easily as a TZ file, you click on it and can visualize it and go through different areas. It gives you a good impression what happens then there in space. Yeah, further examples. So these are from water authorities done. This is from a contract done for water authorities in Germany. This is River Elbe. What you saw here, I will start it again, is all on one day at different times, different satellite takes, and the products are operationally derived. This is suspended matter. For the River Elbe, you see the impact of the tidal effects in River Elbe, and you can, with high resolution data, this is MODIS, with high resolution data you can then zoom into further details. So that means if you have to know about these impacts, if you do construction work on the river, if you do usually hydrodynamic modeling to understand the system and improve the system, this helps you in data assimilation to understand better, to calibrate your models. So that's the way as BRW is working this, or also the authority for inland waters, BFG, is then you're looking for standardized measurements for the river system in Germany. So BRW, for example, uses in the way to understand better the transport processes of suspended sediments, as they have, as usually authorities have here in situ measurements, but no spatial measurements. EFB, so they visited us a few weeks ago. They meanwhile state that this kind of measurements seem to be very harmonized and a very objective measurement, especially in comparison to in situ measurements, because if you have, even in Germany, if you want to measure countrywide turbidity and suspended matter, you still have different measurement systems, different turbidity devices who slightly in a different way measure turbidity and are different way calibrated. So it is usually those agencies don't have a harmonized calibrated measurement systems, and that seems to have much more to work out and get a national and international overview of what is going on in the systems. Furthermore, we have environmental agencies involved in this project who are using this kind of data to measure chlorophyll and again suspended matter. So these are the alpine lakes between Germany, Switzerland, Austria, and Italy. And if you go here into some details, here this is, for example, a long-term time series. You may be difficult to see. Here are some black points in this graph. These are the ground truth measurements, and the colored points are the sunlight measurements of only one satellite system near this. The different colors and sizes means shows the quality that is automatically generated. So as smaller, as lower the estimated quality for this pixel at this virtual station, so at the same station where the authority in the central lake takes the measurements. Essentially, just to summarize it, it shows you already on a long term that this measurement is harmonized. So going to just 1 year, you can easily then derive from these multiple satellite records with one satellite, which already gives more measurement than the authority is doing. Monthly means, which then more direct give you an impression of what is this seasonal way. If you integrate this with different satellites, so this is the same year. You see here blue points. This is Meere satellite. Green points. This is MODIS satellite. You have exactly then the same seasonal trends here in. Of course, you have much more. You see now the high temperature variability, but you see also then that each satellite measurement also has underlying its own inaccuracies. So it is, we can even not no more distinguish than on this level here exactly if we distinguish between 0.1, 0.2 milligram per liter. What is the inaccuracy of the system? What is the natural dynamics of the system? We go to chlorophyll, to a much smaller lake, even just to see what is the cutting edge at the moment. So the Lake Zurich, you see again the black and gray lines are measurements of chlorophyll taken from different depth intervals. It shows you something about the shows the same seasonal trends. So that means we have here a standardized way to measure these parameters. But I should mention chlorophyll is more limited to certain environmental conditions, because if you have very organic waters with high dissolved organic waters, then the chlorophyll products become more inaccurate. So that chlorophyll is more impacted by such things as suspended matter, for example. Here we have one example from a project made for the agency CONAVIO under the Ministry of Environment in Mexico. So algae bloom monitoring, they have a regular toxic algae bloom in the Yucatan island, which causes significant losses for the fish population there. So these are economic losses then already. They try to understand this system, what is going on, because at the moment the topic is to understand. They don't know what to do against it so far. We have another project that is going on, bilateral project going on in Vietnam, led by German Aerospace Center together with different Vietnamese authorities and partners. EOMAP is responsible here for the inland water quality project. They set up an information system which integrates not only water-related topics but all different topics of hydrology, sociology into an information system in order to provide the stakeholders then a better overview over the whole system. Because you might know that here are essential questions, economic questions behind to understand, and this can also only be done if you have the integrated information together. So just some views from the water quality here. So we process here multiple satellite scenes, Iconos, Teos, this is a Landsat on top, MODIS of course. You can go with this into details, for example, of the far upstream to China to estimate quantitatively the impact of certain dams. So this is the Chihuahua Dam in China. It was established in 2009. So these are some scenes here of 2009 from January to November. This dam was then established, I guess, in September, October. You see in November, the dam fills up. The central part is what is the change of suspended matter concentrations caused by this dam, because this has then again downstream impact on the nutrients provision for the Mekong data. So this is time series for taking from only from one point after the dam, from 99 to 2011. I might zoom in a little bit. So you see before 2007 still high seasonal variations. This is only one satellite system again. You can increase it if you have several. So you see the seasonal variations of turbidity through the years. They go already down a little bit, probably due to more further upstream dams. But especially in 2009, so if you look to 2009, after the dam established, the peak in the autumn since that time is no more there. That means there's a significant decrease of suspended matter, and you can quantify this with this method on a long-term scale. But if you integrate further satellites into such an information system, so you see here a map of the Mekong data. Behind here are MODIS products. At the moment only, we go later to integrate this with other products. You can go through these areas and directly see what are the concentrations in space and time. To visualize this, I would like to show you. This is just a QGIS plug-in. So this is a freeware QGIS. If you go, you don't see my hand here that I see on the screen. So do you have a video? On the left-hand side, in this graph, you see units of in milligrams of suspended matter, so between 1 and 100 at the moment. The scale varies depending where we move the mouse to. So I'm sorry that you don't see this, but the cursor here on the screen is currently here somewhere in front of Quoc. So this is Bay of Thailand with low concentration. No? Oh, it's now you see the mouse. So, yes, now you see the scale is between 0.1 and 1, so low concentration of turbidity here, far away of the coast. You see a slightly seasonal trend. Of course, these are quite low concentrations, so there's some variability in this. If you come closer to the coastline, so here this is Nanjia Bay, here. So you see now the concentrations are between 10 and 100. The different colors are due to the different years, which are shown here, 2007, 8, 9, 10, 11, 12. All these single points are monthly means of the satellite measurements that are taken at that point. So that just that you understand, behind this image, there are, I don't know, 50 or more monthly means of the satellite products of turbidity of suspended matter. Let's assume turbidity here. It is all the same physical unit, of course. So at that location, you see then the time series here for year, the green line, the year 2010, the red line to the year 2011, and so on. You can go here in the inland lake, so here, lake over there, you can go here into those dams here. So this is the dam. Here, you cannot see it, it's quite small here, but you can here also clearly see the seasonal trends. Maybe you can go into the river system, and if I make now change a little bit kind of plus. So you see now here the timeline in terms of years, so 2008 to 2012. If you would like, I go now again here into this bay. Well, you can already see some trends. One here, front of the Mekong River, large variability, of course. Yeah. Continue here. Okay, that's what I presented before. If you go now into the river, so this is a point near Canton. So the river has here a width of maybe 1 kilometer. With modest, you reach here the technical limitations, but we wanted to try what are the technical limitations here. That means we have essentially in width only 1-2 pixels available. That means it needs very accurate corrections of atmosphere, land adjacent scatterings, and so on. This is the time series again. Black points are modest measurements. You see clearly the seasonal impact. And the red points are in situ measurements of turbidity. But there are some details behind this. This in situ measurement is not the modest measurement is from the satellite, so it gives you something like a mean value of the mainstream because it has such large pixels. This one here is point-based measurement, somewhere located. It is not located in the middle of the river usually. So there's one device that is located in the central river of Bathymetry stream, so that is here at Canton. It is not in the center, it is on the border, of course, and here is a lot of resuspension, so you see this in the data. The data are much higher. This value is from an adjacent incoming river channel, so it's Canton River, just a few hundred meters inside. That means the essential concentrations change here better with the mainstream than those one that is located there directly on the border on the other river. And, if you integrate this now with further satellites, so these are single shots of Landsat, the blue points. The green points, single shots of rapid eye. There could be more scenes available, but these were those which we organized and processed. And here you see that the temporal shots at one time fit still with this in the range, but fit also show also the same seasonal fluctuations. Of course, they have more fluctuation because here's also the temporal dynamics now, which differs from the monthly means that is shown in here in these lines here. But it shows that this is a harmonized measure between all these different satellite systems. Yeah, well, that means I think then understandable that we can change all the scales now very easy. So from scales covering whole Asia, then into very detailed scales of inland water and river systems or near coastal processes, dredging. Yes, you have this still in mind, so that there are already lots of sensors in space, and there will come more sensors, satellite sensors, that will more exploit than the temporal and spatial resolution of those products. It means in the near future, Sentinel satellite fleet will start end of the year with the first satellite, and the next year with further satellites. So this is from the European Commission investment of its $4 billion US program, which of European Commission, European Space Agency, well, to achieve an autonomous and operational Earth observation capacity, essentially, of course, for the governmental task in Europe. But as companies, we can use these data to exploit this for monitoring of over the whole globe. So there are different satellites behind. I think some of you will know about all these capacities that will come up in the near future, and will contribute to further existing satellites that they are from NOAA, from all the governmental national satellites. And at EOMAP we go now the strategy of implementing our processors as many ground segments on top of the ground segments to allow them harmonized product and production worldwide, so that means we have already installed in Australia, on top at Landgate in Europe, at German Aerospace Centers with European coverage, and Central America for MODIS. We continue this year then with the new Landsat satellite, and we have through the ESA and European program the full access to the Sentinel fleets, and together with SkyMap we will now explore this then to the full capacities, including all other governmental satellites. Of course, there demand some requirements on those satellites, so we cannot use each satellite system. We have some requirements on the radiometric stability. That means the photogrammetry sensor cannot be used for this kind of products, just to be aware of that. And in upcoming months, we will then make this available for clients via web portals like this, easy, directly available. And from that, I think the way is not so far than to bring it then to even end users, to mobile users, to divers, to tourists and so on, because production becomes very effective and the products become then also very cost effective. So that's clear. This is in a project we now run to develop these capabilities. Yeah, well, one last slide for water quality. There's of course a core technology behind this. We have all the software that runs all these processes, but behind is still a very sophisticated physics-based processing chain, modular, that on one hand side with all atmospheric and adjacency corrections over land goes through the water quality product, and another one which goes to the water depth products. So it is sensor independent. So on the one hand side, the physical-based modeling of finite element relative transfer models is stored sensor independent. If we work with specific satellite or airborne sensors, then we create a subset of this database, which is then a global satellite database for a specific satellite. And the processors already automatically adapt them to the different spectral properties and radiometric properties of these sensors. That's the technology behind that, what you saw before. So I would like to give you a view to seafloor mapping and bathymetry is missing here on the title. So what we are doing here. So with the same processing chain, but with the last module that corrects for the water column impact and iteratively calculates water depths and seafloor properties, we create bathymetry maps from various sensors. So it depends on the client's requirements, which sensor, due to spatial resolution and cost, fits here. So it can be done with this case rapid eye. We work a lot with Worldview data. They are very capable, so we are OEM partner of Digital Globe worldwide to market these products. Even Landsat is capable then for 30-meter resolution if this is then adequate for the users further sensors. But still here are the requirements on the sensors are here even much higher because to derive this product you need a very high bathymetric sensitivity and specific spectral questions also on the sensors. But this is Saudi Arabia, Jeddah, just another visualization project that we did here together with ASTA DM data. So, for example, for NOAA, we recently delivered Oyster Virgin Islands in Northern Mariana and Seminole Island. So this is an area of 500, product area is here about 500 square kilometer as a commercial pilot project for them. Looks like that. So these are Oyster Virgin Islands. See over here are between, so the yellow-green tone is between 0, brown, green is at about 10 meter, and blue is at 30 meter. This is the validation plot with those validation data that were publicly available. I thought we have a zoom into this validation plot here. So that means the ground truth data that we could, this historical ground truth data that we had go back, I think, already maybe 1-2 decades. But still, the validation was quite good here. This is a derived biological cover. So, in dependence on the environmental conditions, it is possible to derive seafloor spectral classes and relate this with habitat classes. For sand, it's always very clear due to the spectral properties, but for algae, seagrass, and other benthic materials, then usually you must do this in combination with ground truth data. For Shell, another commercial project for some infrastructure setup. We mapped for them 600 square kilometer, and the savings for Shell for this project were about $1 million because they didn't have to cover this area now with echo sounding ships and had good focus on the relevant areas based on this overview by satellite data. With offshore planning for Tunabio, we mapped last year and will finish in a few next weeks and months the whole Yucatan coastline down to Belize. For them, it's an environmental baseline mapping, so the first coral reef habitat map of the whole coastline. On site on that, we create bathymetry. That's not the main target for them, but for us, of course, to get step by step more off-the-shelf products than worldwide available. For the geological survey in Ireland, we started mapping different bays in Ireland. So this is Wexford Bay. Yes, so we are now here for them at the second contract. This was very satisfied for them with this product. For UK Hydrographical Office, we have done several projects. So one in the Mediterranean Sea, and the comment from them was in comparison to conventional methods, this is 5 to 10 times cheaper than if you do this with other. But especially if there are many areas which are not accessible directly with airborne LiDAR or with echo sounding, so it is still in many areas of the world the only way to derive them in a reasonable time. So it means here in a few weeks' time then bathymetry. Dingle Reef in Australia, this was funded by co-funded by BHP Billiton for an environmental consortia led by CSIRO. So this was 3,500 square kilometer. Again, to create an overview of the whole Dingle Reef, quite large reef. So the first map, I think it was the largest hyperspectral survey. So the base was here, not satellite data, it was hyperspectral airborne data, and to derive the seafloor habitats. Another example, of course, these kind of products can be shown also as the traditional isoline plots, just to demonstrate this. Few validation data, examples from around the globe. So this is ICONOS in comparison with LiDAR. survey in the Indian Ocean. I'm not mentioning where, it was a commercial industrial project for the oil industry. We have, this is another one for another commercial client. This is in comparison with echo-sounding data, so going down here up to 15 meters. This is quite old, so we generated this 5 years ago. This is, I guess, QuickBird based in Rottnest Island in front of Perth, Australia. This is Mexico, Yucatan. And you will see here, these are quite relatively clear waters. So accuracy will go down if you go to more and more turbid waters, so like Irish Bay and so on. This is a clear limitation of this technology. At this stage, we're actually working on further improved methods to come here then down to better accuracy in more turbid waters, but there is a physical limitation, so we cannot with this method go to extremely turbid waters, rivers and so on. Here are some other technologies available which helps you out, but not in this accuracy. So conclusion, with this method you can reach accuracies in comparison with the available validation data between 8 and 20 or 30%. If you want to do a survey in a very turbid environment, the error will further increase. Depth range independent on the conditions, so quite turbid conditions, for example, relatively turbid in the Baltic Sea would be up to 5 meters. For clear conditions up to 25 meters, but this is still the old number. So now for the lower contract we realized we can go down up to 30 meters. There's restrictions that I mentioned, but we have essentially the advantage that we have here a methodology that is very cost effective, can be derived very fast in comparison to to the traditional measurements and worldwide. Well, in combination with radar methods, for example, to derive measuring the incoming wave fields, there are more opportunities, but these are under research. The same as oil spill detection. Just ending this talk with another example of what can derive not only from SAR but also from optical sensors. That goes beyond than what we can do usually. So this is Louisiana oil spill. You might see this. This is only MODIS. We did this for Montana oil spills, also in combination with different other sensors, so rapid eye. I hope you will have some discussions. I'm looking for your questions.
Thanks, Thomas, for the interesting. Now it is the time for Q&A.